Okay, guys, what I want to do here is kind of help you get started on this chapter opening project and make sure we understand what's going on. You can't see anything yet, so let me fix that. Okay. So we're looking at shoe print versus height. And so the data is down here at the bottom of the screen in this, you have this table here. And so what I'd like to do is I'd like to reproduce the table in an Excel file. And so we did this yesterday. So I'll just catch up to some of you guys. You can also do this we showed in the calculator. So you could do it either way, right? But there's lots of software out there that can, oh, now you can't see it again. Did that just go blue? Weird. Try again. Good? So you can see the, okay, here's the chart from the chapter opening problem. They have shoe prints in centimeters and they have heights in centimeters. What I'd like to do is put it into Excel. So I'll write shoe, and I'll just say centimeters. That'll be my first column, and my second column will be height in centimeters. Now I'll just go through. So somebody that has a 29.7 centimeter shoe, we're looking at 175.3 centimeters. Then there's another person with a 29.7 centimeter shoe, and the height is 177.8. So that's a little bit taller. And then we have someone with a larger shoe, 31.4 centimeters, and it's 185.4 is the height. And then we have 31.8 centimeters, 175.3. And then we have 27.6 centimeters, and the height is 172.7. Okay. So there we go. Right. So I have some data. And so now if I want to compute the correlation coefficient, do you remember what the process was when you use Excel or Excel stat? Yeah? Linear regression is what we want, yeah. I mean, that really does it all. So let me open this up a little bigger. And let's go to Excel stat. I have to start mine still. And yeah, I'm going to choose. So if you guys could do this, let's make the shoe size be X and let's make the height be Y. Okay. And we'll go ahead and try to see what we get. Linear regression. And so the first thing that it asks me is, where do you want the Y to be? Well, no, that's not where I want it to be. It's showing all these random numbers from your names. Okay. I was here in sheet 2. I want the Y values to be the heights I said. So that's these. No, yours may look a little different. So if you look across the top on mine, I have something that says linear regression, right? But right. So on the free version, this is what you have. But if you just downloaded it, or if you have the paid for version or the trial version, it's under modeling. There should be something that says mathematical modeling. Do you see that? Yeah. Click on mathematical modeling, and I think you'll find. Do you see linear regression? Yeah. Cool. So that's where we get the Y coordinates. And now for the X coordinates, I want to use shoe size. And so let's see. I don't know what this says. I'm going to delete that. I want to make sure I'm getting the x coordinates to be these shoe sizes. There they are. And I guess that's all I need, and I'm going to press OK. It's going to ask me, do you have 5 rows and 1 column? Yeah, that's what I have. Continue. And it's going to generate a new sheet. And again, this has all kinds of information that we have not talked about. All right? But maybe one of the most important things to see, do you remember where we get the correlation coefficient from? Well, you get it right here, right? Correlation matrix right there. So my correlation coefficient, it says, is 0.591. Now, how do you interpret that? Notice it's in green also. So how do I interpret that 0.591? So yesterday when we talked about correlation, the picture I showed you that I thought kind of summed it up was right there, right? If the correlation coefficient is close to 0, there's no correlation. It has to get into the critical region for there to be a correlation. Okay? I don't know if any of you still have the data from yesterday. Yesterday we also did a problem with the pizza and the Subway fare. You guys remember doing that one? And then my correlation coefficient was 0.988. I guess I don't know for sure, but my memory says when we looked at it, wasn't this written in red, 0.988 yesterday? Because I think what they were trying to do is symbolize that you're in the critical region. I'm tempted to put that data back up here and check it out again. So there's the pizza and Subway fare. Let's play the same game and let's do the linear regression using StatCrunch on this data, and let's see what we get. So let's see, I'll hit linear regression. It's going to ask me, where do you want the data from? So the first thing I want here, I want to use, let's see, the y value was the Subway fare and the x value was the pizza, right? I think that's what we did yesterday. It actually doesn't matter which one you use for x and which one you use for y, because r will be the same. Your graph will look different, but r will be the same. All right, so there, yeah, we had 6 data pairs yesterday. And so let me zoom in so you could see what we did yesterday. Oh no, it's still in green. See, if I were writing the program, I would want to maybe make this red or something if you were in the critical region, right? So how do you decide if that's significant or not? Well, you need to look at the p-value. So somewhere here, they give me the p-value. So guys, to get the p-value, so do you guys see the correlation matrix? The correlation matrix is one of the first things you look at. You go down here, and this number is the correlation between x1 and y1. x1 stands for the, let's see, in this problem, how did we do it? We had x1 standing for the shoe print, and y1 stood for the height, right? So that correlation coefficient is only 0.591. That's not very close to 1. And as a matter of fact, your p-value, they give down here, it's always in this analysis of variance. And you'll see this row that says model. If you go to the very end here, that is your p-value. It's 0.294. Is that low or high for p-value? That's pretty high, right? For it to be low and reject the null hypothesis, that would have to be smaller than what? Yeah, whatever the significance level is, 0.05, or sometimes we've used 0.01. That's high. So yeah, we fail to reject. Now what is it that we're rejecting or fail to reject? That's what we have to get across today, I think. Because in the pizza problem, here's the pizza problem. Check out the p-value for the pizza problem, guys. It's right here. 0. I mean, is it really 0 or is it 0.0001 or something? It's really small, right? Now, why is that? Here, take a look at the pictures of the graphs, right? When you look at the p-value data plots, look how closely this line goes through those points. It's not perfect, of course, but it's close. Whereas if you compare to what we just did, look at the data we just did for shoe size versus... You see all this big gap here between the point and the line? And here's another big gap between the point and the line. And that was the best they could do. The linear regression line is the best line you can have going through your data. It's not very good. So, did they come up with a model? Yes, they came up with a model. But it's not a very good one, right? It says here, where's the model at? They give you the equation. Oh, right here, right? So y1 is 125.4 plus 1.72x1, right? That's the line they graphed. But I guess my point is, guys, when you look at the problem on the board, and I ask you, is there a correlation between shoe print and the height? My answer would be this: no linear correlation, 2 R's, sorry, exists. Okay? So no linear correlation exists. So there was a follow-up question I asked you guys to the chapter opener. And that was this. Suppose a person has a height of 200 centimeters, right? And so the question I asked was, what is our best estimate of their shoe size, shoe length, in centimeters? Yeah, what's our best estimate of that? Well, I guess the first point is, don't use the linear regression line. Here. Don't do it. Because we don't think that's a very good model. Okay? So, again, maybe flashing through some of these slides actually might be useful at this point that we didn't get to yesterday. We got to these, and I said we got to this, right? The only time we know we have a correlation is if R is really close to 1 or really close to -1. But we have R is, for this problem, is like 0.53 or something, 0.35, I forget. It's somewhere in the, it's not in the critical region. So I'm not going to use the linear regression line in that. I mean, you could compute one, but it'd be a bad idea to use it. That's kind of what we're saying. They give another example. This interpretation I want to get to in a minute. You know, have you guys seen in your book how they always have a part 1 of the section and part 2 of the section? Part 2 is usually for a more advanced course. All right? And I've been skipping it almost every time. But today, in linear regression, I actually think it's worth looking at part 2 because of what you guys have done and what you understand. Again, we wish to determine whether there's a significant linear correlation between two variables, right? That's the problem I just asked. Is there a correlation between shoe size and height? But we're going to do it more formally now with a hypothesis test. Now, wait a minute. You guys know all about hypothesis tests. Usually, the very first thing you do for a hypothesis test is you make a claim, right? Right after you make the claim, what's the next thing you do? Null hypothesis and alternative hypothesis. Give me a sample null hypothesis. What's an example of a null hypothesis we've had? I know it has to have equals. What else would you write? Mu equals something, right? 42, or sometimes we did like mu1 minus mu2 is 0, right? But we did 2 of them. So yes, we know all about that. And that's where I feel this part 2 helps you understand correlation because of what you studied. Okay, guys, they say n is the number of pairs of sample data. Yeah, I know that. They say r is the linear correlation coefficient for a sample. And then they say this Greek letter is the linear correlation coefficient for a population. Right? Do you remember what that Greek letter is, by the way? I mentioned it once. Yeah, I did. It's called rho. Let me write it down for you so you know it. So, if you guys look here, oh, I got to come back to this problem too. Yeah, I have a few things to do with you guys. If you guys come here, okay, so I guess what I'm saying is we can do linear correlation more formally using a hypothesis test. And I just think this is a really nice way to kind of wrap up the course. Is you're using this one more time on a new statistic and parameter, right? So my statistic is going to be R. My parameter is the Greek letter R, which is called rho. It's usually written that way, R-H-O. But the symbol that they used in Greek was this. So if you ever see that curvy P-looking thing, that's the letter rho. It makes the R sound in Greek. So what we have, okay, is we're going to have a null hypothesis and an alternative hypothesis. What do you put in the null hypothesis? Do you put the statistic or do you put the parameter? Think about when you did it with means. What do we put in the null hypothesis? The statistic, yeah, we put the parameter, don't we? Because we usually put mu, right? So what I'm going to do here is the null hypothesis is going to be that rho equals 0. Now, rho equals 0 would mean there is no linear correlation. Okay? And rho does not equal 0 right? So this is going to be a two-tailed test the way I'm doing it. What would this mean? This would mean that there is a linear correlation. But here's the thing, guys. We don't want to use the linear correlation line unless we're sure, or at least reasonably sure that there's a linear correlation. I guess you can't be perfectly sure, but we want to be pretty confident. And so that's what's really going on here. And so, okay, a couple things you need. You need a simple random sample. Well, yeah, we've needed that every single time. Visual examination of the scatter plot must confirm that the points approximate a straight line pattern. Yeah, don't try to use linear regression on a parabola, right? Or something else. Make sure it's a line. And then number 3, the outliers must be removed. Yeah, we talked about this yesterday. Okay, so here is what I just told you. And you either reject H0, and if you do reject H0, then you say there is sufficient evidence to support the claim of a linear correlation, right? So when they did the pizza versus Subway problem, they computed their test statistic. Oh, they actually use a t-test. Look at this. They actually compute t equals, and they base it off of r and r squared. We're not going to do all this, guys. I just wanted to show you that you can go through the same kind of things we did. Hey, guys, t equals 12.7. Is that a big T value? It certainly is, right? If it were a z value, we'd say, yeah, that's really big, and so your p value is really small. I think we got 0 on the computer. And so we reject H0. We say, I think there is a, you can also have one-tailed tests. All right. All this is beyond what we need. But I just thought it might be worth showing you so you understand a little more of what's behind R. When you compute R, guys, it's not magic. I mean, there's a formula behind it. But what you're really doing is you're saying, hey, is R close to 1? Then yes, then I'll use the linear regression model. If R is close to 0, I'm not in the critical region. It's really estimating rho is what it's doing. Okay, so back to my follow-up question. How do you answer it? I told you how not to answer it, right? I mean, we had this data. Let me get the data back up there for a second. We had this data about shoe prints and heights, right? And so I went with Michael Jordan. I said, hey, I have a 200-centimeter person. Can I predict the shoe print? Well, if you had a model, right? If you had a model, then you could use the linear regression line. I'm saying don't use the linear regression line here. Again, why? Because the p-value is too large. So then what do you do? Well, the question was, what is our best estimate of the shoe length? Well, if you don't have a correlation, the best estimate you can do is to use the mean. That's the best estimate I have. Because if there's not a correlation, then his shoe size could be anything. Okay? Now, it's interesting. Because if you ask me, hey, I have someone that's 200 centimeters tall, so that's Michael Jordan's height, I'm going to guess foot size is a little bit bigger also, based on what I know, right? But if we don't know anything, the best we can do is compute the mean. And so what would I do? Well, I guess I would take the mean of these 5 values right here, right? 175, 177, 195. So maybe it's about 180, right? Now we could compute it. I don't feel like doing that right now. Okay? So again, if you're in doubt, I guess the best we could do is use the mean. Okay? But if there is a linear correlation, then you can use the equation. We were doing that yesterday. Let's go back to that problem from the book. It was problem 16. And because we were rushing, I kind of screwed up here at the end, and so I want to fix that. All right? So in problem 16, we worked out, and we got this as our model using Microsoft. No, I think we used the calculator for this one. Is that right? Let me double check. Maybe I still have that. But while that's loading, let's turn to problem 16 in your book. Let's see, what page was that on? Oh, thanks. Yeah. So on page 528, if I go down here, 529, really? Yeah, this is the one where we talked about altitude versus temperature, right? And so I think we have this data in the calculator. And if we do, I think I'll punch it up again so we can look at it. So let's see. If I look in my lists, let me see what I have. Edit lists. Yeah, that's it, right? At 3,000 feet, the temperature was 57. At 33,000 feet, the temperature was negative 54 degrees. You guys remember this? So if it's in the calculator, do you remember how to get the linear regression model? Under tests. So we're going to hit Stat button. We're going to scroll to the right. We're going to hit Tests. But I want to show you something you can do that I didn't do yesterday. Okay? No, I don't want a z-test. Sorry about that. Let me try that again. Hit the Stat button. Go to Tests. Oh, do you remember where it is? If you hit the up arrow, you're almost there. It's the second from the bottom. It's choice G. Oh, no, wait. That says linear regression T interval. That'd be a confidence interval. We want linear regression T test. Let me go up to F. See the difference? So if I hit that, it's going to ask me a few things. Where's your X's in list 1? Where's your Y's in list 2? And see, now you guys understand what this is saying. This is saying, hey, we understand this is really a hypothesis test, rho. What I didn't tell you is about beta. Well, I'll let that go. Okay. But rho is really what you're estimating. The other thing I didn't show you yesterday, and I'd like to show you, see where it says regression equation here? I think this is a really nice feature that the new calculators have that the old ones don't. If your calculator is new enough that you see this option, regression equation, I would encourage you to do this, guys. What I'm going to do is I'm going to tell it where to put the regression equation. I'm going to write y1 in there. Let me show you how to do that. Do you see this key we've been pressing a lot that says VARS? That stands for what? It actually stands for variables. Okay? Yeah, usually what we've been doing is hitting second, right? What's above it is distribution. But what I want to do is show you that all the different variables that are in this little computer are all listed here. And if you go to the right where it says y variables, it's helpful to put the regression equation into a function. Number 1, I'm going to store it for y1. And I'm going to calculate. You might say, well, Paul, why'd you do that? Well, because yesterday, when I wanted to do this, right, I had to, I wanted to write down our answer, right? So I wrote down y is 72 minus 3.7x. And then if I wanted to graph it, would you guys know how to graph this line? How do you do graphing? Yeah, if you go to the calculator and you want the calculator to graph, you hit the y equals button. So I'm going to do that. I'm going to hit the y equals button. Well, what happens is, because I told it where to put it put it in for y1 already for me. I don't have to type it. So that's kind of nice. So now, if you want to see what the line looks like, you can hit the graph button, but you're not going to see very much. I mean, here's my graph paper, and I don't see it. Oh, there you go. But that's not a line. Of course, you're not seeing that at all, right? Must be I have a parabola in here from a previous class. That's what I think. Oh, yeah. Look down here, y5. Look what I have. y5 equals x squared. Well, let me get rid of that. But why didn't we see the line? Well, see, now I'm tapping into your algebra days. So do you remember this algebra? You guys, when we graph a line, let me go back to the graph. When you graph a line, the form we usually use when we graph lines, let's see if you remember this from ages ago. Do you remember y equals mx plus b? Oh, you do. Okay, so what's what in this problem? M is the slope. That's right. B is the y-intercept. That's right. So what is the slope of our line? Well, you'd have to take our equation and write it in this form. So really what we ought to do is we ought to rewrite that as y equals, see that the slope is always in front of the x. So it would be negative 3.7x plus 72. Does that make sense to you guys? So what's the y-intercept? The slope is negative 3.7. The y-intercept is 0,72. The reason you didn't see the line is because when you just graph with the normal window, it only shows you from negative 10 to positive 10. And so I'm going to hit this window button up here. And I'm going to change my window. Now the x's are okay, but the y's we have to change. So let's see, I'm going to make the y min, I'll keep it at negative 10. But y max, how about I make that 100? And y scale, I'm going to put a mark every 10 so I can kind of keep track of what's going on. What this does, this changes what the window is that you're looking through when you look at the graph. See? Now I can see it goes right through 0.72 like you guys said. You guys understand that? I mean, there's a reason that we require Math 0850 before you take this course, because otherwise you wouldn't have any idea what I'm talking about, right? It's all about this line. Okay, so now what? Well, now I'd like to see how the line goes through the data, right? And there's a way to do that which I think is really cool. So what you can do is you can do what's called a stat plot, okay? And so you see y equals, but also up here it says stat plot right above. So to get that, I'm going to hit second y equals, and it says stat plot. Plot number 1 is off. Well, I want to change that, so I'm going to hit enter. And it asks you, what do you want to do? Well, I'm going to hit enter. I want to turn the plot on. It asks, what type of plot do you want? Actually, we did some of these a long time ago. Do you guys remember what this one is? That's a histogram. And how about one of these? This one was your box plot or your 5-number summary. Anyways, you can do these things, but we're going to keep it where it is. A scatter plot is exactly what I want. This dot plot. It says, are the x's in list 1 and the y's are in list 2? Yes, that's what I have. It asks me, what kind of marks do you want? This is all good, okay? So when you're all good, well, you could press graph, but graph won't show all of the data. Again, because my window's not right. Although I can see a little bit of the data. I can see it going through, right? So the trick, if you ever want to see all of your data and you have a stat plot, is you come over here to the window. Oh, no, not the window. I'm sorry. you hit the zoom button in the middle. This is the fast way to change your window. And do you see down at the bottom, choice 9 says zoom stat? If you select that, it'll zoom in wherever the data is, and it'll show you what's going on. So you can see we have a pretty good line here, right? Actually, I don't remember. What was our correlation coefficient? We should check that. Let me go back to, well, let me do the stat plot, the test one more time. So I'll hit stat, I'll go to tests, I'll go up to choice F, linear regression t-test. Let me do it one more time. Yeah, calculate. Because I just don't remember what the p, oh yeah, the p-value is really small here, right? So this is a very good model. And that means you can answer questions using the model, okay? So here I go, guys. The question that I wanted to ask was, well, it's written here. Let's look at the book again. Because this is what you guys will be doing for homework tonight. You'll be graphing lines, you'll be plotting points, but then you'll be answering questions. How does the result compare to the actual recorded value of 48 degrees? What result? Oh, this one. Find the best predicted temperature at that altitude. At what altitude? At, 6327 feet. Right? So how the author recorded the temperature, I have no idea. Must have been in an airplane somehow. Right? I don't know, maybe it was on a mountaintop. Might have been on a mountaintop. There's mountains that go that high. Is he from Denver? I can't remember. Anyways, so if the temperature there was 48, well, that would kind of fit in here, right? So the question is, what's our best predicted temperature at 48 degrees? Well, we can use the line, right? Because the correlation coefficient was really close to 1. The p-value was really close to 0. So let's compute it. 6327 feet, right? So to find the predicted temperature for 6,000, what was it? 327 feet. Use the equation, and what will we substitute? First of all, should that go in for x or y? That's important to understand. Yeah, I listed that up above, right? One of the first things I did, and I would encourage you to do that on your homework. Write down what x is and write down what y is. So what are we going to substitute? We're going to say x equals, now what I'm going to substitute in would be 6.327. Why did I do 6.327? Yeah, I mean, if you look at what I wrote, x is altitude in thousands of feet, right? So this means 6,327 feet. But yet, that's the number you have to put in for x. So how do you do it now? Well, two ways. One is by hand. You could say, well, I'm going to take y equals negative 3.7 times 6.327 plus 72. Right? What would be the next thing you would do? Well, you would do the multiplying, and then you would add on the 72, right? You guys know how to do that. Or you can use technology. And this is something I've been trying to get you guys to do. So, on the calculator, this is actually really cool. If you already have it in what? In the y equals screen. If you already have it here, and you have a graph, right? So here's your graph, right? I mean, you could actually plug in 6.327, and that's the output right around there. Have you guys ever, when you've used the graphing calculator in the past, I don't know how much you have, this button here says trace. This is really kind of cool. If you hit the trace button, it puts you on the data points, right? And if I hit the right arrow, oh, this will go from data point to data point. But if you want to go on the line, you can hit the up arrow. And now I'm actually on the line. You guys see that? So I could just keep going back until I get to around 6.3. Well, that's pretty close. It says at 6,000 feet, the temperature is 50 degrees, right? So we want 6,300 feet. Well, I can't get it exactly this way. But there is a way to get it exactly. Instead of hitting trace, I'm going to hit second trace. Do you see what's written in blue above the trace button on these calculators? It says calc for calculate. This is a really cool feature. Calculate a value. I press enter. What do I type in? It says, what do you want x to be? You can type anything you want that's in the picture. 6.327. Right? Enter. There's the temperature. 49.18 degrees. Okay? So, I wrote that down, 49.18 degrees, which is what you would get if you calculated it by hand. And then the homework asks, how does this result compare to the actual recorded value of 48 degrees? That's pretty close, right? I mean, it's 1 degree higher, right? So that's not too bad. Guys, one other issue about the chapter problem today, and I should mention this. Remember the follow-up question I gave you guys? Suppose a person has a height of 200 centimeters, right? I said, what's our best estimate of the shoe length? And I said, well, we can't use the regression equation. But even if you could use the regression equation, you might not want to here. Because it is dangerous to move beyond the data of your regression line. It's a mistake you see happen in statistics quite often. It's okay to do, but you should realize that you can get very bad results. Like, suppose I asked in this problem, look at this data. What would the temperature be at 90,000 feet? I'll tell you what. It would be dangerous to plug 90 in for x into that equation. Why would it be dangerous? That would be what's called extrapolation. Extrapolation is trying to use a regression line beyond the data set. Do you understand what I mean by beyond the data set? I mean like higher than the highest point or lower than the lowest point. What we did here, when we plugged in 6.327, I mean, this you might call interpolation. Interpolation is just fine. Extrapolation, that's a little dangerous. I mean, if you think about it, guys, if I said, hey, what's the temperature going to be 90,000 feet? I am not confident that it would follow this straight line pattern once you get up to that high. Because wouldn't you like be beyond the ozone layer at that point, right? And basically be in outer space, right? Your temperature would go down really quickly once you get out of the atmosphere. I understand it's getting lower and lower and lower as you go up, but I don't know that it's going to follow a straight line. At some point, it's going to change to a curve. Does that make sense to you guys? Okay? So you do have to be careful about that idea as well. Okay, so number 13. Listed below are annual data for various years. The weights of lemons imported from Mexico and U.S. car crash fatality rates. What? I thought when they said lemon, I thought they were talking about, you know how you call a car a lemon? I don't know. They call it a lemon if you got ripped off, basically. Yeah. Now that's a good question. Why do they call it a lemon? I don't know. That's a good question. Is there sufficient evidence to conclude? Oh, get out of here. If there's a correlation, right? What is this? The tons? Metric tons of lemon imports and the crash fatality rate? Did you get a correlation here? You got a correlation? I have to do this. You guys want me to do this on the calculator or computer? Okay, let's do the computer. So here we go. We're going to plug that data in to Excel, and we're going to see how this all works. You did it on the calculator? Let's try the computer then, okay? Because you got to do the computer for the project anyways, so. All right, so I'm going to do, okay, metric tons of lemons. And then next to it, I'm going to do, what was the other thing? Oh, it was the U.S. car crash fatality rate. So car crash fatality rate. This is ridiculous. All right, so here I go. I have my columns. I want to, it didn't work. I want to look at the data here. So let me minimize this guy or bring it over or something. Okay. Metric tons of lemons and the car crash fatality rate. So one year we imported 230 metric tons of lemons, and the car crash fatality rate was 15.9%. And then we got more lemons, 265, and we were at 15.7. 358, and there's 15.4. 480, 15.3, and then 530, 14.9. All right, so there it is. So I have the data. So now, let's see. Go to Excel Stat, hit linear regression. That'll do everything I want. Okay, it says, where is your data coming from this time? So, I guess this time my Y values I want to be the car crash fatality rate, so I'll just do that. And the X values, I'm going to make metric tons of lemons. This is a ridiculous problem. Continue. Okay, let's see if we have a correlation. So where do I look? I have to look at that correlation matrix. So let's see, that's down below here. Right here, correlation matrix. Oh wow, look at that. What do you think, guys? Do we have a correlation?
Yes.
Well, it's pretty close to -1, right? I guess the question is it close enough to -1? And you have to either know the p-value or the critical value, right? What's that? You have a critical value? Where'd you get the critical value from? So the critical value you can either get from, there's a table in the book, or the p-value, it says, we can look at that ANOVA table. So let me go down to where it says analysis of variance table. Yeah, 0.01. I guess there is a correlation. Weird. All right, let me go back to the problem. So according to my calculations here, right, is there sufficient evidence to conclude that there is a linear correlation between weights of lemon imports from Mexico and U.S. car fatality rates? Yes, there's a correlation. Question number 2. Do the results suggest that imported lemons cause car fatalities? That's a big no. That's a big no. The point of this problem is interpreting the linear correlation coefficient. And I know that some of this is small and hard to read, but I believe they make a big point here. Common errors involving correlation. It is wrong to conclude that correlation implies causality, right? There's a correlation between lemons and car fatality. Okay, fine. But that certainly does not mean that lemons cause car fatality. Not at all. I mean, it could be this, guys. Maybe as the years go by, we're importing more lemons and there's more car crashes. Or maybe as the years go by, we're importing more lemons and there are less car crashes. But that doesn't mean that one causes the other. So please understand, right? Well, it's a nice example because we know this is not the case. And yet, I think it says something about the power of graphs. Guys, don't you think there's people out there that are going to pick up the newspaper and if they look and they see, or on their news story on their phone, they see this graph, and on the bottom here it says lemon imports, and on the top over here it says car crashes, and they see how close the data points are to the line, they might say, oh yeah, so it's lemons are causing car crashes. No, they're not. They're correlated. They're not causing it. So do understand that about this. And I think that's the whole point of that problem. So yeah, then I guess on tonight's homework they're going to ask you to use one to figure out the other. Suppose you know the number of lemons. Can you figure out how many car crashes there are? That's funny. Jawan, I'm glad you brought that up.